studies of temperature and most, or to be more precise, the change of temperature, and then there's something wrong in that equation. It's the letter C. In physics books, actually, the way we write it is in a lowercase, but that's fine. At the end of the day, the equation is what matters, and I don't want you to understand heat as just that equation that depends on the change in temperature or the mass or what that value of C means, which is the specific heat capacity. You have to understand heat as the transfer of energy from one substance to another. When you have a substance that is warmer than another, like the example I gave you last class with a piece of iron that is warm on the stove, for example, right? And then you put it on top of ice. Then there is a transfer of heat from one substance to the other, in this case from the iron towards the ice, right? So that's a way to understand heat, is the transfer of energy. The other way is by doing work, which increases your internal energy, right? So we also discuss the meaning of heat within the first law of thermodynamics, where heat is equal to the work done or by the system plus the change of internal energy. All of those variables can be either positive or negative. We do have a sign convention for work and for heat. When heat is added to the system, it's positive. When it's removed, it's negative. So think it this way. If you have iron and you place it on top of ice, hot iron, the ice melts because it's getting heat, it's absorbing heat, while the iron is losing it. So at some point, they will reach what we call thermal equilibrium. It's the point where the temperature of the system is the same. Right? Sorry about that, guys. Who is calling at this time? Wait a second, guys. Oh, it's a scam. Can you believe it? Okay. Okay. So, what are the parameters for heat? You have the mass, you have the change in temperature, and we have the specific heat capacity. We already know what mass is, right? It's the amount of matter or the amount of stuff in a body. Or, in terms of Newton's second law, is the resistance to an acceleration. Okay. What is change? What is temperature? Temperature is the average kinetic energy of particles. Particles will move faster if they are at a higher temperature. But what is the letter C? What is a specific heat capacity? A specific heat capacity depends on the substance. I want to show you guys a table after this, so actually take a look at that. Different materials, substances, they have a different value for the specific heat capacity. So look at the units. It's measured in joules per kilogram per Celsius. So the way we define specific heat capacity is as the energy required by a substance to increase by 1 kilogram of a substance to increase its temperature by 1 degree Celsius. I'm going to go at it again. The specific heat capacity is the energy required to increase by 1 degree Celsius 1 kilogram of a substance. So, what is that? What does that mean? It means that for example, for water, it takes, okay, that's wrong by the way. Okay, that's because it says pure. But in general, for water, the specific heat capacity is 4,186 joules per kilogram per Celsius. Okay, those constants are always going to be given, so that's fine. But what's the meaning of that constant? It means that it takes 4,186 joules of energy to increase 1 kilogram of water by 1 degree Celsius. That explains a lot. That explains why water can be used as a nice coolant for cars. That explains why it takes so much time for the water, not just of the lakes, but for any type of water, if you put it in a kettle, to boil. That explains why the ocean, even on the summer, can warm and can take such a long time to warm or to cool down, right? For example, if you guys go to the beach in June, and I did this, the water was really cold. It takes like 2 or 3 weeks within June, almost at the end of June, for the water to be at a temperature where you can actually go in the water. That's because water takes a long time to increase or decrease its temperature. And that's very important. We have discussed water as a fluid. We have discussed water now as a liquid in this case. And we also discussed it as a liquid when we did buoyancy. So the density of water is important, but so is the specific heat of water. Now, if you compare it with other substances, now you understand why, for example, lead or copper or silver, why those materials can heat up so fast. If you put a cup of iron or a piece of iron on top of a Bunsen burner that you use in the chemistry lab, you will notice that after a few minutes, it's already hot. That doesn't happen with water, right? When you want to boil water on the stove, it can take what? More than 5 minutes. It can take up to time, depending, sometimes 5, 6, depending on the amount of water, of course. So it does take more time. That's because, as you can see, the amount of energy to increase iron or copper or silver temperatures by 1 degree Celsius is much less than water. Okay? Let's do, okay, so today I uploaded the weekly problems for this chapter. I'm gonna be honest with you guys, we are almost there. This is the last section where we have calculations. And there are a lot. So most of the guide is about calculation, or most of the calculation problems, right, that you have in that guide that I uploaded just a couple of hours ago. It's about problems of this, because there's a lot of situations. So let's remember here, that is specific in joules per kilogram Celsius. You know what? You can find this also in joules per kilogram per Kelvin. And it's the same value. Because the change, especially for water, right? Remember, the temperature, as you go as you go high and high or low and low, the 273 difference becomes irrelevant. Now, you can also find, for example, for water, you will see that you can find that the specific heat can also be 1 calorie per gram per Celsius. You know what? It's amazing. because it takes only 1 calorie, but this per gram. So using this, remember, right? For water was also 4,186 joules per kilogram Celsius. So if I multiply by 1,000 grams here, I get 1 kilogram here. So I can certainly say that 1,000 calories are equivalent is like that, to 4,186 joules. So then if I divide by 1,000, 1 calorie is equal to 4.186 joules. So when you go to the gym and you burn 200 calories or 100 calories, you are, well, for 200 calories, you are almost in 1,000 joules. The thing is that, for example, a pack of cookies or a piece of chocolate, you start with, for example, I have here, let's see. This drink has 220 calories per serve. No, 80 calories per serve. So actually I think in this one it has 220. So this has 220 calories. Right? So that means by drinking this guy, I get that amount of energy. So look how much energy I get. I get almost 1,000 joules. Right? You don't get the same with water, by the way. Okay? Now, what gives calories? What increases the amount of calories in the food? One of the ingredients is sugar. Right? So for example, Coke will have way more than that, than Gatorade. As you increase more fat, right, you start getting, but we do need calories. It's just that we have to be able to measure how much energy we output and how much energy we input, right? But that's a nice conversion there. So everything that comes in calories is a unit of energy, right? Now, let's take a look at a few problems. So one problem can be if they give you simple, they can give you 2 kilograms of, or 2.2 kilograms of water, right? So let's do that here. They want to know how much heat you need to increase the temperature of water by 80 degrees Celsius when you have 2.2 kilograms of water. So how do you do that? So let's say they gave you, this marker is there. They gave you 2.2 kilograms of water. And normally you have to put here the specific heat capacity. And they want to know how much heat was Q. You have the mass, you have the specific heat, you have the change on temperature. So Q will be mc delta T. mc delta T. So that will be 2.2 times 4,186 times 80. And you will get a lot. In joules, you will get a lot. But obviously, we change it to calories. we shouldn't have to do, but you get a more realistic value. So you get almost 740,000. You get this value. 736,000 736 joules. To get it in calories, I will divide this by 4.18, right? So just so you know, I will get 176,000 approximately calories. So that's not that bad. And the thing is that now we can apply the ideas of conservation of energy. When we talk about Newton's laws and mechanics for falling objects, for a mass on a table that I'm pushing, we neglected friction. But I did mention that realistically speaking, there is always some sort of friction going on between masses, whether you push or you pull. That friction is computed by a force, the force of friction. But that friction does some work. We know that the force, the work done by friction. But what is work? The change of energy. So the energy due to friction, which is the work due to friction, it's normally released in form of heat. The best example would be in a collision. In a real collision, we don't have conservation of energy. Some of the energy is lost in terms of sound or friction, which is heat. So we can use the mechanical part that we did and get the amount of heat, for example, of the Niagara Falls. Or let's just keep it simple. Let's suppose I have a mass of 5 kilograms and I'm going to drop it from certain height. If I assume that when the mass lands towards the earth, which could be the case of a meteorite, and then when it crashes towards the earth, we call it a meteorite. That energy is transferred in form of heat, and then you have a crater. So, well, in that case, there's some kinetic energy, right? Because a meteorite is traveling with some speed. Here, I'm just going to drop a mass for certain height. The idea is that all the potential energy is transferred into heat. So we need to know what type of material it is. So let's suppose I give you a mass of copper. So I have a mass of copper that I'm dropping from certain height. Let's keep it easy and let's say it's 10 meters, okay? Okay. Let's say this is 5 kilograms of copper. We need a specific heat, which is approximately 390 joules per kilogram Celsius. So when the ball reaches this point, all this energy, the potential energy, you're gonna have heat. This heat, because of conservation of energy, of course, we're still neglecting the air friction, right? But that's fine. All this heat will be basically the potential energy, which is what? mgh. But let's suppose I have the temperature of copper. Okay, so we are going to, or actually, we don't even need a mass. Let's suppose I want to get the change on temperature, not the heat. If I want to get the heat, I just use this equation. So gravity was 9.8, right here. Uh, 490. So this will give me 490 joules. Perfect. So I got the heat. But now, let's suppose they ask you for the change on temperature. For the change on temperature, that's when you will need the specific heat capacity of copper, which you already know is 390 joules per kilogram per Kelvin. So if I use this, I can get that 490 joules is the mass of copper, the specific heat of copper, times delta T. And as you can see, it's not going to be much. If I do the calculator again, I get 0.25. Very tiny. All right, it will have to be dropped from way higher, and it will have to be a. It will have to be. No, the height is the main thing. The mass is irrelevant because if you think about it, right? The mass will cancel when you do mgh equals to mc delta T. So it's mostly about the height. Or it will have to have some sort of kinetic energy, right? Let's suppose you have your car, and then the tires are moving at very high velocity, and if you all of a sudden you brake, that will create more friction between the tires and the ground, and of course we will get more heat. So let's do an example like that. For that, I will use one of the problems that I uploaded today, because today I think I put quite some in there, and it might be like you need help to understand some of these system problems. So there's a problem here. This is it. Change on Fahrenheit to Celsius, so that's fine. There it is. That's a good one. And actually it's very realistic. A 6.5 gram iron meteor. So normally asteroids and meteors are made of rock and metals like iron. So that's good. Hits the Earth at the speed of this. If its kinetic energy is entirely converted to heat in the meteor. So actually, this explains why some meteors not disappear, but they disintegrate as well. Not just in the atmosphere due to friction and heat, right? But also when they crash towards the Earth, they release so much energy that is absorbed by the meteor that it can cause part of it, depending, right? Because rock has a very high melting point. Part of it might melt. It depends on the velocity and also depends on the mass of it. Anyway, how much will its temperature rise? Right? Ooh, they give you the specific heat of iron in that form. So this is a problem. That's an interesting one. I'm gonna unshare this for a bit. I'm gonna put it here. So these are the type of problems that you, and I want you guys to focus on this because I noticed in the quiz that the concepts are more clear, although I know that it's open book, so I know that you guys have access to that, but with the problems it's different, right? You won't find the problems anywhere because I made up my own problems. They are similar to the ones that you can see in the worksheet, right? Like the Pascal principle or in the lecture notes. But I made up my own situations. So be careful with that, okay? We will go over a few of those probably on Tuesday before the quiz for this chapter, okay? Which is next Thursday. Remember that, okay? But just look at how I do these applications. So they give you a mass of iron and the speed of the meteor of iron, and then it crashes towards the earth. So they're asking you, like what we did here, the change on temperature. Now there is no potential energy, now it's kinetic. So when a meteor crashes towards the earth, like that, the kinetic energy is going to be fully transformed to heat. And we know the equation of heat is that mc delta T. So technically we don't need a mass, right? What we need is the specific heat of iron, which is given, and the velocity of the meteor. So let's see that specific heat. They tell you that the specific heat of iron is 113. So you put here C of iron kilo or calories? Calories per kilogram per Celsius. You know what? You don't want to leave it like that because the speed is in meters per second, right? So if the total kinetic energy is going to be transformed to heat, which is that, then 1/2 mv squared is equal to mc delta T. Mass cancels, so the parameters to know the change on temperature are this and the speed, which is 295 meters per second. Okay, we just have to change this. That's why they tell you that calorie. 1 calorie is 4.18 joules. So I can convert my specific heat from joules to calories. From calories to joules, sorry. I can do this. 113 calorie per kilogram Celsius. You can do 1 calorie, 4.18 joules. So calorie cancels, and then you get that 113. We did units conversion, right? So you should know, you should remember 472 0.34 joules per kilogram Celsius. Now I use this. 1/2 of v squared equals to that, which is this, times change of temperature. So in that case, the change of temperature will be greater, right? Because now we're dealing with a more realistic case, with a meteor. Ooh, again 92 degrees. The change of temperature will be of 92, so almost the boiling point of water, but not close to the melting point of rock or iron. All right, which is around 700 Celsius, approximately. Okay, so that is a nice example there. Okay, conversion of energy. But is that the only thing that we deal with? Not really. We also can deal with concepts of thermal equilibrium. Let's see what I have here. So there's a problem there, a different type of problem. So remember that the idea behind the last example was to show you how natural satellites, but also with our artificial satellites, they normally disintegrate when they enter the Earth's atmosphere. That's because of friction, right? That goes into heat. I think we talked about this already. So I have already discussed the fact that water has a very high specific heat. So that means that water, all right, can absorb or release large amounts of internal energy, and then it won't cause a huge change on its temperature, right? That's why, as I said, water can be used as an excellent coolant for engines, for many industrial processes. It's also a good solvent, as you know, right? Now, water can circulate around different areas of the engine, right? And it can absorb the heat from another metal, normally a hotter metal, and then cooling the other parts. So that's amazing, right? That's great. And on top of that, we know that the boiling point of water is 100 degrees Celsius and 0 Celsius, the freezing point. All right. Remember that this table for the next question I want to ask you. Actually, there it is, right? So the specific heat of copper is 390 and of steel is 460. So copper gets warmer faster. The lower the specific heat, the faster it heats up or cools down. A 10-gram piece of copper heated to 50 degrees Celsius will feel hotter in your hand than 10 grams of silver also heated to 50 degrees Celsius, even though copper and silver conduct heat equally well. Well, almost equally well, right? There's a difference. What's the difference? Why does a piece of copper will feel warmer or hotter than a piece of silver? What is the difference between them? Anybody? The reason is not conductivity, by the way, because they both are equally good conductors. The reason why you see that change is because of the specific heat capacity. The specific heat capacity of a material creates that change in how you feel heat being transferred from one object to another. The amount of internal energy that a solid object will have gained in order for its temperature to rise at a certain amount depends on what? So the internal energy, all right, in this case only depends on the mass of the object. All right. For heat depends on what material is made of and how large the temperature change will be. Internal energy is just about the mass, okay, of the system. The temperature of a moving baseball increases as it is cold. What do you think? Think about the problem of the meteor. The temperature of a moving baseball increases as it is cold. True or false? Anybody? It's true, right? The reason why sometimes it can even hurt a little bit is because of not just the force exerted due to the baseball on your hand, but also because of the heat release. The kinetic energy of the baseball is transferred to thermal energy, heat. And one reason water is useful for cooling is because the specific heat capacity is relatively low. False, it's because it's high. Okay, so let's talk about thermal equilibrium. Imagine you have a cup of water. Water at room temperature, 20 degrees Celsius. And then you place a piece of copper or iron or silver, which is very hot, into the water. What's going to happen with the temperature of water? What's going to happen is that the temperature of water will increase. All right? So if the temperature of water is going to increase, what can we tell about the water itself, the iron? The iron will lose temperature. So that's how you can understand this situation. Now, in the lab, and this is the topic of the lab, I'm pretty sure, you guys will do a situation where you will have a piece of, at least that's what I do for a specific heat capacity. You will place a container with water, not like this, but it's a proper calorimeter. That's the thing about that. We're going to be using a proper calorimeter for this. Well, that's in the lab. I don't think we have one here. But the calorimeter, or actually it will be there, right? You will use a electric kettle and you will boil water. Well, you will try to get it as close as the boiling point as possible. So as close as 100 degrees. But there is a catch though. Inside the water, there's going to be a piece of iron or copper or aluminum. So we know by the zero law of thermodynamics that if two substances are in equilibrium, they are sharing the same temperature. So because the water and the piece of iron or aluminum are held together inside a container with iron inside the water, then it makes sense that we can consider both to be at a thermal equilibrium. So when you are boiling the water, they both reach the same temperature. Now, why do I do that? Because now in the calorimeter, so in another container that we call a calorimeter because it's a perfect insulating device, you will have cold water at 15, 16 degrees Celsius. Once the water boils with a piece of iron, you will move that piece to here, the calorimeter. You will close it and you will let it there rest for a little bit, a few minutes. Then you will use a thermometer, digital thermometer, and you will measure the temperature change of water. Let's do the experiment. Here, I want to give you some numbers. And then we can go into phase transitions, and that's it for today's class. And the thing is that we are basically at the end of the chapter, right? What we will do next class is just a few applications, and then we can review a little bit of what we've talked about in this chapter, which you can tell is not very long, and then discuss about the upcoming quiz. So I have here water, and I'm going to introduce here a piece of iron. And you know what? Actually, wait. Let's suppose that you don't have iron there yet. You have water at a temperature of 20 degrees Celsius. And the mass of water will be of 0.6 kilograms. So 600 grams. I'm going to boil water with iron. And once the iron is hot enough, I'm going to place the iron inside the water. But the temperature of iron, I'm going to say is around 98 degrees Celsius. And on top of that, I'm going to say that the mass of iron is of 80 grams. I want you to find the final temperature of the system. So that's a key problem I want you guys to understand. Find the equilibrium temperature of the system. So at what temperature these substances reach equilibrium? In the lab, you're going to measure the temperature. In the lab, your aim, your goal, will be to compute the specific heat capacity of iron. And obviously, you're going to do percentage error, right? So this lab, depending how you do it and depending on the tools, can work out very smoothly. But sometimes, and I used to do this in the high school, depending on the element and depending on the students as well, to be honest, the experiment can throw you very random numbers. Like, for example, the specific heat of iron is 460. I remember last year when I did this with the kids, we got less than 400. We had to repeat the experiment, and then we got it better. Because you know what's the key? Is how you measure the initial and final temperatures. You have to be careful with that. There it is. Okay. So, how do you solve these problems? The technique that I always like to show is this. You're going to do a line. You're going to say that you have water here. And water is at 20 degrees Celsius. And you're going to locate iron here. Iron is at 98 degrees Celsius. By logic, the equilibrium temperature will be in between. Let's suppose it's here. We're going to call this T. So, there is a principle I want you guys to remember from the conservation of energy. The heat gained by water is equal to the heat lost by iron. What's the heat gained by water? The mass of water, a specific heat of water, change on temperature of water. For iron, will be the mass of iron, the specific heat of iron, times the change on temperature for iron. So water for iron. The mass of water is given 0.6. We know the specific heat capacity of water is 4,186. All right. Change on temperature of water. You want to look at the figure. The final temperature of water was T. The initial was 20. So what do you write here? T minus 20. What about for iron though? Here is where students tend to make mistakes. The mass of iron, 80 grams, that's 0.08 kilograms. The C of iron is 460. But look, what is the change of temperature for iron? Iron started at 98 and it became T, but it went down. You know what you write? You write 98 minus T. All right. So now I have everything I need. Let's do some calculations. I think that what you need to remember in this problem is the distributive property. We're going to distribute that in a bit. So, okay. There. There. And then the algebra will be this times this, minus this times this, and here will be this times this, minus this times this. So you will get this, a linear equation, not difficult. minus, so let's use this again, there it is. So these numbers will give you the following. $53,838 equals to that 48. All right, so we divide 53,838 divided by 2,448. We get 21. That's amazing. The temperature that you get is 21.1 degrees Celsius. So you know what? The water went up 1 degree, 1.1 degree. The iron went down approximately 79 degrees. You know why that's the reason? Oh, sorry, 77, right? The reason is because water has a much higher specific heat. Even though it absorbs the same heat, it doesn't get that much higher in terms of temperature. All right? So that's a very interesting exercise there. All right? I will invite you guys to try and do some of those problems. I will try and do them, well, let's see, in the weekly problems. There is a problem like that where they give you 50 grams of lead, all right, at 100 degrees, same problem, all right? They give you 50 grams of lead, you're going to put it into 75 grams of water, and they want you to find the final temperature of the mixture. The only thing you have to be careful here is the specific heat capacities. You want to change them. Actually, you probably don't even want to change them because they have the same unit, so they will cancel. So it works out very nicely. Okay. All right. Now, that's thermal equilibrium, by the way. Okay. That's a nice problem of thermal equilibrium when you have two or more objects, right? One going into another in a substance. It can be water, it can be lead and water, or it can be water and water. Hot water into another container with cold water, and they reach equilibrium. Okay? Okay, so let's take a look at the consequences of heat, change on temperature, and specific heat capacities. The follow-up for this will be phase transitions. So, last chapter, when we started to talk about the physics of matter, we introduced the 4 states of matter, right? Solid, liquid, gas, plasma. And we know there is other ones like neutron stars and so on. But within the three main states of matter that we study here on Earth, which is solid, liquid, and gas, there are processes in which water can solidify, can also evaporate, and then condensate in the atmosphere, right? And then produce the clouds. So, how much energy is needed for water to boil or to melt, in case of ice, or other elements, right? Why some elements do not melt at the same point? Because the melting points and freezing points, they depend on the elements. It can be iron, it can be water, right? It can be lead. So, what are the conditions for a phase transition? You have to reach, by adding heat or removing it, certain temperature. When you add temperature, guys, you are increasing the average kinetic energy of particles. When water gets to 100 degrees, it reaches a flat line. I think I showed you that, guys, in the heating curve. Water does this, and then it reaches a flat point. During that flat point, you have to add more and more heat to break the bonds. Let's imagine you are actually trying to melt ice. You need to increase the potential energy of particles as well. So that's the key. The key for a phase transition is the potential energy of particles, which is measured by the forces, intermolecular forces that keep molecules together. You can break that bond apart, and then you can have a solid becoming a liquid, and you keep breaking apart, they become a gas, steam. So there are two main processes that we can study using formulas and equations. One of them is the vaporization, and the other one is fusion, which is melting or solidification. Why do we use both? Because normally we apply this for water, but this can be applied for any other element. So ice can melt and then can become water, and then water can vaporize into steam. And then we have the inverse processes like condensation, sublimation, solidification, and so on, right? Let's take a look at the slides so you can know where to find this information. Oh, it's taking some time now to go into screen sharing. Remember, guys, the class is recorded, but if you have any questions, please let me know. All right? Oh, great. What's happening with the sharing? Is it something I did here? Okay, that's fine. Let's try to just show you guys. So in the slide on phase transitions, you will have the name for a few of them: boiling, melting, condensation, and freezing. And it shows you what happens with the internal energy. All right. This is the thing though. I said last class that internal energy is the addition of the kinetic energy and potential energy of particles. Now, the concept is okay. You increase internal energy when you boil, when you melt, and you decrease it when you condense, when you freeze. Freezing is solidification, water to ice. what's going to happen in a few weeks or months during winter. Okay, there's something wrong right now with this. Okay, whatever. So when we reach a flat line in a phase transition, the temperature remains constant. So I wasn't explicit on this, but the kinetic energy of particles, actually I was. The kinetic energy of particles depends directly on the change on temperature. So if the change on temperature is 0, the particles are not having any change on kinetic energy. That means that the consequence of this internal energy increasing is that the potential energy of particles is the one that is changing. All right? So let's suppose you have a glass of water and you have that in the stove and you have heat being transferred. All right? The temperature will be increasing steadily until it starts to boil at around 100 degrees, right? Or 100 degrees Celsius. So even though heat is continuing to be transferred to water, no more energy can be added, kinetic energy, to the molecules. So what's going to happen now is that you're going to start to break the bonds that hold the molecules into the liquid state. So you have a phase transition. Below the boiling temperature, the water molecules are bound to each other. During the boiling, the molecules are already giving enough energy to break the bonds. You increase the potential energy, and then this actually starts producing the phase change from water to gas. A similar process happens when you melt a solid. The atoms and molecules go from being rigidly bound to start being loosely bound. All right? Condensation and freezing, however, are just reverse processes. From being apart, you start putting them together. All right? And the energies are the same. It's too bad I cannot show you this curve. Sorry guys, there's some problem here with the system to show you the slides. But in the slides of the chapter, when you go to phase transition, then you go into latent heats. So let's show you the board then. I can do this on the whiteboard. Latent heats and phase transitions. So I'm going to redo the heating curve. At least for water. Normally it should be heat per temperature. Alright? But I'm just going to do it easier for you guys to see. The same temperature and heat. I'm going to start with ice at negative 10 degrees Celsius. This is the melting point, and the boiling point will be around here. It's not to scale. All right. The units are Celsius. You put ice on the stove. So ice will start here increasing its temperature. At this point, at 0 degrees, you keep adding heat. It's melting here. Once the whole ice has melted, it starts going into water. This is the solid state. This is melting. This is liquid. It reaches another flat line. And then it becomes what? A gas. it is, let's use the same word, boiling. The more technical word is evaporation, but it's fine. And then it becomes what? Here, gas. We know how to calculate the heat in the solid and liquid state. The heat is mc delta T. But there is a new form of heat for melting and for boiling. That's called latent heat. Latent in English means hidden. Why is it called hidden, latent heat? Because there is no change of temperature. So how come there is heat? Because that heat doesn't depend on the particles moving. It depends on the particles. It depends on the particles breaking apart. Latent heat equation is the following. The latent heat equation is a constant that is called L times the mass of the substance. So normally we call it like this. We call it QL, latent heat equals to L times the mass, where you can have latent heat of vaporization, which is boiling, which is the mass times LV, or you can also have the latent heat of melting or fusion, which is MLF. Let's put the keywords here. Fusion is like saying melting, and vaporization, well, that's more obvious, right? Is boiling. I'm gonna leave it like that, guys. We're basically done with the chapter. The only thing left is to do problems on this, all right? And then maybe talk a little bit about thermal machines, but that's not really one of the goals for this. We won't talk about humidity. Don't worry about that. I think the main part on this chapter is these phase transitions, the first law of thermodynamics, linear expansion, all right, the coefficient of linear expansion, and then what do we talk about? And then, the concepts of the scales of temperature, all right? The way of sign is very simple, all right? So try to pay attention when I do the problems on Tuesday on, oh, by the way, it's election day. So please, if you guys cannot make it, let me know, all right? I will make sure I record the class, but I will be here. I don't vote, so I don't care. But if you guys have to vote or something, let me know, okay? But we will have a revision class, and on Thursday, you will have the quiz on this chapter, okay? All right, guys, I'm gonna stop the recording.